Hello, we are the Michigan Mars Rover team. Our team of 120 dedicated members has been hard at work redesigning our rover, applying valuable insights from past competitions. In addition, we've placed a strong emphasis on outreach and integrating new members through hands-on projects. We are so proud to introduce you to our 2025 rover.
This year, several improvements have been made on our rover to address failure points seen in previous designs. We are continuing with our welded aluminum torsion box chassis and internal differential bar, which have been further optimized for mass and structural rigidity. Our suspension has been completely redesigned to a double lambda rocker bogie design to improve obstacle traversal capabilities while maintaining greater contact with the ground, allowing us to maneuver through a rock garden and climb slopes up to 30 degrees. Along with this, we have further refined our tire design and custom drive gearboxes, utilizing brushless motors to optimize traction and maneuverability. Our 5 degree of freedom robotic arm has also been improved upon. We are continuing with a prismatic base joint for ease of operation, along with custom cycloidal transmissions for our heavy-duty joint. Our differential wrist combines 2 degrees of freedom into a tight package. We have built 2 new end effectors, which have been uniquely designed for the equipment servicing and delivery missions. All joint positions are monitored using a combination of encoders and limit switches.
Our sample acquisition system involves a sheathed auger mechanism that plunges 10 centimeters into the soil. Attached to this system is our temperature and soil moisture sensors. Once collected, the soil is dispersed from the auger using a gear differentiator and can be cached in a sealed container. The soil is also directed via peristaltic pumps to our instrumentation and sample handling system. A Benedict solution will test for the presence of reducing sugars in the soil, and an anhydrous dye test will inform us of the presence of polypeptides in the soil sample per sampled site. In addition to our biomarker detection, the rover performs a series of habitability assessments with a sensor suite assessing UV index, oxygen presence, and ambient temperature. To further geological understanding of the sites, a series of onboard cameras visualize the surrounding cliff sides for stratigraphic profiles and search for signs of aquatic erosion. A mast gimbal is further used to take panoramas of our sites.
Compared to last year, our electrical system is now more centralized. We've developed and upgraded several of our custom boards. First, a new brushed motor controller is capable of operating 3 individual motors. Next, our science control board has been modified to power heaters and manage various new sensors. In addition, control of the autonomous LED board is integrated into the upgraded power distribution board. For onboard communication, we use CAN due to its reliability. Additionally, we've upgraded the CAN transceiver hardware to support 5 megabits per second across all boards, significantly reducing operational latency. Our rover's communication system operates at 2.4 gigahertz, and we've improved our base station antenna to be more directed with a higher gain of 20 dBi. This enhancement extends our communication range up to 1 kilometer and allows for operation even without a direct line of sight. Powering the rover is a 36-volt battery mounted beneath the electronics box, providing at least 1 hour of uninterrupted operation. For safety, an emergency stop button is positioned on top of the e-box.
The software codebase this year was migrated from ROS 1 to ROS 2 and is tested extensively using our in-house simulation environment. We have newly deployed custom position and velocity-based inverse kinematics on our robotic arm for precise operator control. For autonomous typing, a neural network-based letter recognition and segmentation model is used for closed-loop visual servoing between keys. Our autonomous navigation system has integrated optimal path planning using stereo camera data for cost map generation to avoid dangerous terrain. The perception system has been deployed on a camera with a zoom lens to detect the mallet, water bottle, and Aruco tags from longer distances. We have iterated upon our existing TensorRT GPU-accelerated object detection pipeline by diversifying our training datasets, including artificially generated Blender model data. Our dual antenna RTK GPS localization system has been optimized with new hardware and is fused with IMU and magnetometer data using an invariant extended Kalman filter for centimeter-level localization precision. Our new features are rigorously tested in simulation and include failure detection and recovery behavior to ensure the robustness and reliability of our software stack.
We practice continuous integration at the subsystem level in order to emphasize on-rover testing. Practice and mock missions allow us to prepare for the competition environment, while operators can become familiar with mission strategy. Additionally, a drone is used to assist in looking for objects and reading signs for the delivery mission. We're confident in our ability to succeed at URC and appreciate your consideration.